part of our solutions chapter has a redox component where we look at solutions that have equations in them, or that have equations that have elements that are reducing and oxidizing agents. So we need to review this. I know you guys did this in your other classes, but there are some definitions you need to know. When we talk about elements, we have elements in our redox systems that can be reduced and elements that can be oxidized. When we talk about oxidation or reduction, we're talking about oxidation or reduction of single elements, not a full compound. Okay? By definition, when an element is reduced, the oxidation state is reduced. Element reduced, charge is reduced. So if the oxidation number goes down, it's reduction. If the oxidation number goes up, it's oxidized. Now you might have learned it in terms of electrons, oil rig, oxidation is losing, reduction is gaining. That's fine and all, but I think it's confusing to think about losing electrons and what does it actually do that makes you go up in charge. That's confusing. Think about it in terms of charge or oxidation number. Oxidation number goes down, it's reduction. Oxidation number goes up, it's oxidation. So whenever you choose what's reduced or oxidized, they have to be individual elements. In order to identify these in the equation above, we need to figure out the oxidation states of everything in there. Copper solid. All solids or elemental things have what oxidation state? 0. If you have an ion, the oxidation state is the same as the charge, so it is +1. Now we got to break down these elements. We know that oxygen is always what? -2. So if oxygen is -2, what does nitrogen have to be for nitrate to have an overall of -1? +5. Nice. So nitrogen on the other side is the product in nitrogen monoxide. Well, let's go back to oxygen then. -2, so that is +2. Hydrogen's +1 here. Oxygen's -2 there. Copper's ion makes it a +2. So looking at that, what element is reduced, meaning what element goes down in charge? Nitrogen. So the answer to this is nitrogen. What element is oxidized or goes up in oxidation state? Copper. Okay, so we know how to define those. Now some crazy person out there decided to talk about reducing and oxidizing agents. This is not going to be on the test in 2013-14, but it's on the test next year. They're taking this out of the curriculum. However, you guys get to get tested on it for the last time ever. The agents. The oxidizing agent is the full reactant compound containing the element what? It's backwards, bastards. The element reduced, exactly. That is so not right. Why did they do that? So basically, the agent, the oxidizing agent, is there for oxidation in the other species. It's an agent for oxidation in the other thing. It itself contains the element reduced. So what does that tell you the reducing agent is? No, I don't want an actual thing, I want a definition. It's the reactant, and it's the full reactant compound, not just an element. I want whatever's in the equation, the whole thing containing the element. The reactant compound containing the element, what? Oxidized. So with that being said, oxidizing agent, what compound on the reactant side contains the element reduced? We know nitrogen's reduced, so what's the whole thing? The whole thing. What's that called? Nitrate. That is the agent. Okay? The reducing agent is the whole thing, the whole reactant compound containing the element oxidized. Well, if it's only an element, it's only an element, so the answer is copper. But I do expect to see the entire reactant compound on your test. Okay? You can turn the fan on if you want. Good? Moving on. Okay. Now, these are reactions that need to be balanced. You might be able to sit here and try to balance this using inspection, the way you learned how to balance equations in Chem 1 with blah, 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 blah. But it makes it a lot, it's going to take you a lot longer than doing this half reaction method. Also, sometimes there isn't enough stuff on both sides for you to balance anyway. You're missing waters, or you're missing H pluses, and there's no way for you to balance it. So we're going to balance this using this half reaction method. The half reaction method depends on the redox, the reduction and oxidation. And the first thing we need to do is identify what two things are changing oxidation state. Look at oxygen last. What two things are changing? Sulfur and nitrogen. So we're going to pick one. What do you want to work with first, sulfur or nitrogen? I don't care. Sulfur. So I'm going to pull down everything that has sulfur in it. Sulfur -2 going to sulfur 8, S8. So I am now going to balance this using the half reaction method. There are steps, and I'm going to write the steps on the side that we can do every time we're balancing a half reaction. The first step is to balance everything but H's and O's. All right? So let's do that. Balance everything but H's and O's. How do we do that? There's no H's and O's there, so what do we balance? The S. So we put an 8 here. The next step, balance O's. If we had any, we balance O's with water. Well, there are no O's in this, so we can move on from that. The third step would be balance H's with H pluses. We don't have to do that here. And the last step is to balance charge. What do we balance charge with? With electrons. You can add electrons once to one side to get the charge the same on both sides. So there is a way that you can remember this using a little saying. Angry orangutans hate cheerful elephants. Balance all elements but oxygens and hydrogens. Balance oxygens using water. Balance hydrogens using H+. Balance charge with electrons. All right? If you want to do that. So this one, all we have left to do is to actually balance our charge. So what's the overall charge on the left side? -16. We have 0 on this side. I can add electrons once to one side to get an overall charge of what? What do I do? We're going to add 16 electrons to the right, and now we have balanced half reaction. So let's do the next one. We are going to take down a nitrogen, NO3, going to NO2. Anything that has that element that's reduced or oxidized in it, we pull down. So now we're going to balance everything but H's and O's. Done. Balance O's using water. How many what side? 1 water here gives us 3 O's on both sides. Balance H using H pluses. How many what side? 2 on the left. Balance charge using electrons. What's our overall charge on the left? +1 and a 0. So to make them both the same, add 1 electron. I'll do it here. +1 electron. So that is now a balanced half reaction. In order to add these up to get my full reaction, I have to have lost and gained the same number of electrons. In the top equation, I lost 16, but in the bottom I'm only gaining 1. So I need to multiply the bottom by 16. And in doing so, I end up with 16 here, 16 there, 16 there, 16 there. Oh, not 16. This is 32. Duh. 2 times 16 is 32. 16, 16, 16, and 16. All right. If I did my job correctly, my electrons will be on opposite sides of that sign, which they are. So my electrons always cancel. I never have to add them up. If they don't cancel, I did something wrong. So I'm going to rewrite what I can. I have 32 H pluses plus 8S minus 2s. There is no rhyme or reason to the order you have to write this stuff. Gives us 8 S's, S8, plus 16 NO2s, plus 16 H2Os. That is a balanced overall reaction. One thing you need to check, do you have anything that's the same on both sides? Do you have water on both sides? No, you're good. Do you have H pluses on both sides? No, you're good. The only last thing to look at is little instructions here. They're saying that you need to have done this in an acidified solution. To be an acidified solution, we need what floating around? What does it mean to be an acid? H plus. Are there H pluses floating around? Bingo, we're done. If that were to say basic, we're going to add one more step to it, and we're doing that in the next example, okay? But because it's acidic, we're done after doing it this way. Let's do the next one. All right. What two things are changing oxidation state? Manganese and iodide. So which one do you want to do first? Manganese. So we'll take out anything that has manganese in it. Oops, not plus. Goes to MnO2. All right, I know it says basic, but we're going to do everything the same until the very end. So just do what we did before. Balance everything but H's and O's. Done. Balance O's with water. How many what side? 2 on the right. Balance H with H pluses. How many what side? 4 on the left. Balance charge. Our overall charge on the left side is what? Our overall charge on the right is 0. So I'm going to add electrons to one side once to make these balance. Where do I add how many? 3 on the left. So that gives me a 0 on both sides. All right, now we got one half reaction done. Let's do the other one. Balance. We're going to look at what element again? I. So we're going to take I minus down and IO3 minus down. Balance everything but H's and O's. Done, right? Balance O's using water. How many what side? Balance H using H pluses. How many what side? Now, overall charge. -1 here. What here? +5. Electrons once to one side to make them the same. You're not getting them back to 0. You're just making them the same. 6 on the right. And we're good because we're adding them to opposite sides. So in order to add these up, I need a common factor of electrons lost and gained. So what am I going to have to do? Good. Multiply the top by 2. So I end up with 6, 8, 2, 2, and 4. Okay, let's add these up. We can cancel immediately electrons. So I get 8 H pluses plus 2 MnO4 minuses plus 3 waters plus an I minus gives us 2 MnO2s plus 4 waters plus IO3 minus plus 6 H pluses. Now I'm going to have to clean house in this one. In the previous problem, we didn't add H pluses or waters to both sides of that sulfur one. So we didn't have it show up on both sides of the equation at the end. So we didn't have to do what I call clean house. In this case, we did. And if you noticed, we have waters and H pluses on both sides. That's a dirty house. We got to get rid of enough waters, for instance, to not have it on both sides. How many waters can I subtract from this equation? 3. If I get rid of 3, I have none left here. And how many left here? 1. So we got to clean house. Now, what about H pluses? We're going to get rid of 6, because if I get rid of all of these, it leaves me with 2 there. So I'm left with 2 H pluses, and you don't have to rewrite it here if you don't want. I'm doing it for clarity, because we're about to take into account our basic solution. All right, So I'd say I'm done, but right now, do you see how we're in an acidic solution? Okay, that's not good. This problem's saying we want to be in a basic solution. So rather than doing what the book says by changing the whole procedure early, we're just going to do one additional step at the end. We're going to add enough OHs to both sides, because OH minus is basic, right? To both sides to tie up our H pluses. How many would that be? We're going to add 2 hydroxide ions. Whatever we do to one side, we have to do to the other. Okay. What does 2H plus 2OH make? 2 waters. So we actually here have 2 waters. Do you see how now we have OHs instead of H pluses? So do you see how that's basic? Okay. But now do you see something we have to do? We got to clean house again, right? Because we have waters on both sides. So we're going to get rid of 1 water, leaving us with 1. And the good news is your OHs and waters need to be on opposite sides at the end. Your H pluses and waters need to be on opposite sides at the end. So we know we did this right. So our final equation is water plus 2 MnO4 minus plus I minus gives you 2 MnO2 plus IO3 plus 2 hydroxides. And that is our balanced half reaction. Okay? When you do your homework on these, some of them you'll be like, what do I pull down? This is weird. I don't know how to do this. A couple of the homework problems are giving you equations that aren't net ionic. Make sure you get rid of all your spectators before you start to balance. Okay? Those are for homework problems. Okay. 17, 18, and 19, unfortunately, because I really want to go over in detail this whole concept of titration to get you prepared for the lab tomorrow, we're going to do these as review before your quiz on Thursday. You have a quiz Thursday and a test Friday, is that correct? Test Monday? What are we doing Friday? Oh, we're labbing Wednesday, Thursday, quizzing Friday, test Monday. Okay, so we're going to do this on Friday. These you've already done. These problems are just making solutions and volumetrics from a solid and using a dilution. You've actually already done this. I just threw a couple extra in there. And this to me is the penultimate problem. This problem basically has every concept that could be tested on in one problem. So we're going to do this again as well before your quiz on Friday. How many of you guys are missing Friday? None? All right. Good. So what I want you to do now is, this is the picture that's in your Prelab. If you haven't downloaded your Prelab yet into your iPad, you do have to do that tonight for homework if you haven't started it. But this is the problem that is the Prelab question. For people at home, I'm going to talk about the calculations and how to do the calculations for this titration first. Then I'm going to turn the video off and show you guys the hardware over here and show you how you need to set up the stuff, because that's the part that's kind of tricky. All right. So this is an example of a titration curve. This is specifically kind of mimicking the titration curve you guys are going to be dealing with tomorrow. The mill of titrant. Titrant is what you have in your burette. So you're going to have your burette, and you're going to have a beaker. And in your beaker, you have a pH sensor attached to one of those little LabQuests. And the LabQuest has a screen that's producing the graph as you titrate. Okay? In the burette, you have sodium hydroxide. It's a 0.1 molar sodium hydroxide, and you know that because you're told that. You're going to fill it up to the 0 mark. We have in our beaker HCl of an unknown concentration. We don't know its molarity. You will have pipetted, using a volumetric pipette, 10 mils of HCl in here. You will have then put a bunch of water in there. It doesn't matter how much water you put. We're basing our calculation off the 10 mil of HCl we put in there. And you're adding water enough to cover the bottom of your pH sensor, which is crucial. You're going to have a little magnetic stir bar in here. A little magnetic stir bar is going to be whirling around and around and around. And you got to be careful that the stir bar isn't whacking the side of the pH sensor, because there's a little glass sensor in there that can break really easily. Okay? So You're going to get that stirring. This is filled up to 0 with sodium hydroxide. And then you're going to start the titration. Again, we know the concentration of this. We don't know the concentration of HCl, but we know how much you put in there. So you're going to start. And this is a measurement of pH. And right now the pH sensor at 0 mils of sodium hydroxide added is sitting in acid. It's a pH of 1. Does it make sense that an acid has a pH of 1? Yes. It's a really low pH. So if you notice, this is kind of a crazy person's chart. Every single little fleck is a data point that was collected. You're not going to have to collect that many data points. But you're going to want to collect quite a few data points along the way. And you're going to do so, and you're going to see that you're not going to get a lot of pH change for a while. I might give you a clue within 3 or 4 mils maybe. We can kind of, because we don't really even know the concentration of the acid. Ms. Rozier and I really don't. We have a ballpark idea. We just kind of threw some stuff in there, and it's like, oh, well, we'll see what happens. We'll hopefully give you within a 5 mil range where this sharp rise is going to happen. But you're going to be adding a little bit of base, recording a value of mils, adding more, recording, and then you're seeing this graph come along. And all of a sudden, bam, the pH is just going to skyrocket. This point right here, which is the middle of the sharp rise, you'll either take this point and find the average, or you can use some calculus. What's this in calculus called? The derivative. Okay, you can do that. There's also a way to, they have this little function in the LabQuest where you can take the slope of any tangent line to any point. So you can get pretty close using that. There's different ways you can find this point. But at the end of the day, this is called the equivalence point. And at this point, this is the number of mils of base that you needed to get to the point where, whoops, moles of H plus are equal to the moles of the base you added. Right now, this is a simple titration curve. This is strong, strong. We're going to be talking about strong, weak titration curves when we get into the spring. But let's talk about now how we do these calcs. Well, at this point, I know these are equal. If I know how many mils of NaOH I used, and I know the molarity of NaOH from the beginning, what can I calculate? I know molarity, and I know mils. Moles. I'm going to first calculate moles of NaOH. Once I calculate moles of NaOH, what does that also give me? Moles of H plus, because they're equal at the equivalence point. Right? Moles of known, moles of unknown. Now I'm looking for, the goal is to find what again? Molarity of my acid. So how do I go from moles of acid to molarity of acid? Divide by liters. Which one do I use? How many liters of acid did I use at the beginning? Remember I put that 10 mils in there? So 0.01 liters. And that will give me the molarity of the acid. So that's the calc you're going to do 3 different times. Tomorrow I only expect you to get through 1 titration, and then I expect you to do 2 the other day. And all you need from all this work is the number of mils it takes to get to the middle of the sharp rise. That's it. Once you have that value, you can do all your calculations. Okay? Any questions about calculations before I go into a hardware explanation? All right.